gaming chair. This is usually used for Fortnite gaming, but now today for some Clojure coding. One thing, can you set up so that I can actually share my screen? For some reason, it's not possible at the moment.
Now you should be able.
Yeah. Yes. Just a bit of what I'm doing currently. I work as a lead software engineer in a company called Tomorrow Tech, a small startup company where we build digital products. Our first product is Dias, which is a real estate trading platform used in Finland for, therefore the website is only in Finnish, for selling and buying apartments. So basically the users of the systems are consumers who sell and buy apartments in Finland, and then real estate agents, and then all the major banks in Finland who then use the system for making the payments and all the, let's say, process connection between different banks and sharing the data and so on during the trading process. This is also in Finland, but one thing in Dias is that behind the scenes it actually uses distributed ledger technology, which is actually private blockchain or enterprise blockchain or whatever you want to call it. So this is a small connection to my presentation. We are using a product for this blockchain functionality, which kind of works, but the biggest problem is, of course, that it's not written in Clojure. So today, my goal is to write one new blockchain system in Clojure in REPL. So at least most important parts of it. Let's see how it goes. Usually the live coding might not work that well, but let's start the challenge. First of all, if you think about blockchain, what is a blockchain? There's like what is important to know in this presentation, that the blockchain is actually, there's no clear definition of blockchain, but here are a few things that describe blockchain. It's a distributed database, it's immutable, it's append-only database, and it's also tamper-proof. So it's typical that there are some kind of a cryptographic functions used for making sure that if you have a copy of the database, there is a possibility to actually validate that the contents of the database are correct always and nobody can change them. And then what is this private or enterprise or distributed ledger technology? I think the biggest difference compared to something, for example, Bitcoin, is that this is a permissioned network. So in here, the parties who make transactions between each other, they know each other. You are not trying to make transactions with anybody without knowing who they are. And then there is somehow at least some semi-trust level. But let's not go into details of what that means before we have some code. So in a blockchain, we are storing a chain, which is effectively, you can think it as a linked list. So if I would start writing a very simple function for generating one transaction to the database. Would enter some data there, and since this is, as I said, linked to the list, we then want to know what was the previous one so that we can actually link it there. So, and of course, in Clojure, we use map for this. It's a good idea to just have some timestamp there. I'm using just standard stuff found from Java host language. Then we can store the actual data, like this was the data, and then we want to store the link to the previous one. And in blockchain, we want to actually store it as a hash. So we actually want to store the preceding hash to the blockchain. And the way we take it, we take the hash of the previous transaction and put that into the blockchain. And then it's typical that it works in a way that we actually store some kind of a block there. This is the block, and then we actually have also headers. So let's not think about how to calculate the hash, but then let's imagine that we have always hash in the header, hash of this block, and then we have a reference to the block. And okay, and now something about the tooling, which I'm not going to start the war against Emacs and Vim. I happen to use Vim in this case, and the important thing in here is that if I now generate transaction, let's say one, and this is, let's not put any previous, and when I call the eval, you should see the result in the bottom of the screen. Okay. Then this transaction, which doesn't have the previous one, is called as a genesis block. That's like the starting point in this blockchain, and all the rest of the transactions are based on this first genesis block. And there are usually some special mechanisms for how to start the blockchain, and I'm not going into the details of that in here. But now what we need is actually that in here we want to actually calculate the hash. I think it's not good use of time to here investigate how to use libraries. So I have prepared some good storage of good code, where I have some functions for these kind of things. So I have a function here for actually calculating the SHA of string, and for that reason we need to serialize our block as string, and we can use just serialize, and then let's use this very this is not very enterprise ready, but we can use PR to just turn this one into the serialized form. So now we can actually calculate the SHA and put it in the header. So SHA from serialized block will be entered into our blockchain. And now then actually this hash now. And now if we start creating actual block chain here, like let's create, this is now genesis block, and we can generate now a new transaction on top of the genesis block. And now this new transaction actually has the preceding hash inside the block. And since we have the hash calculated from the block and the preceding hash is inside the block, then we can be sure that actually this new transaction was actually really linked to this previous one. And of course, the next thing is to somehow validate transaction. Transaction hash will be just if we just take in the transaction, and then we can check that actually the hash we have in the headers equals the hash found in the block. So, or like the calculated. So we take the block and here serialize it and calculate the hash, and this should match. So if we now want to validate this, then it should be valid. So now we have some really basic validation for this. But of course, the next step is to validate that the actual whole chain is linked correctly. I'll just check here that like if there are any questions. Okay, let's move on. So now let's think about how to validate the whole linked list here. So let's create these two transactions. This is a just call this the transaction. Now we have some kind of a chain here. Okay, and we can actually just create the let's use this list, so it's easier to prepend things here. So our chain is actually list in this way. And now, if we want to validate that this whole chain is correct in that sense that the preceding hash it always is actually the hash of the hashes match inside the block and in the headers. So let's do, for example, recursive loop transactions from the chain, and our exit criteria would be let's first do this. So now we want to always validate two transactions, so current one and the previous one, and do the comparison there. So we can destructure here the first and the second item of this list. So this would be current transaction, and then this one will be a previous transaction from the transactions. And let's assume that, as I said, we trust the Genesis block. So if we are already, in our case, the previous transaction is nil, then we know that this chain is valid. Then we need another if. So if that's not the case, we want to check that now the now we have to check that two things match. So if we take the preceding hash from the current, of course we have to do it it's inside the block. So if we take the current transaction, then we take the preceding hash, and then sorry, current transaction, the block, and the preceding hash. And we compare that to hash of the previous transaction. Then this is good stuff, and we can actually recur with the rest of the px. If not, then we can return false and put some lot of parents there and hope this passes. Okay. Now this we can loop and check that all the transactions pass, this linked list thing pass, but actually, of course, we wanted to use this validate transaction hash function here so that we actually check that this transaction hash was calculated correctly from the block, and we can just use here the validate transaction hash current transaction, and then in here we need this one, and yes. Now this passes, and basically now we could extract this as function. So let's let's move some place, and this will be called validate chain, which is actually just a link this list. And yes, and now in here we can actually use the validate chain function to validate that actually our chain is valid. And now if we enable this one, this should be true. And of course we did this quite fast, and we don't have tests, but we can trust enough in this case to our blockchain and move on to the next feature. So now we have this is now immutable tamper-proof database, not distributed yet because we are not sending those transactions to anywhere. But you can think that now we kind of have multiple separate processes that share these transactions somehow, and then they can all do the separate validation. But then we wanted to have a network where we can actually know the parties that we are actually making transactions with known parties. And for that, we can use another cryptography thingy, which in this case could be digital signatures. There's quite a lot of boilerplate for this. Let's copy paste. So what we actually are now doing is that we will set up private keys and public keys, and we'll sign the transactions. And for the sake of so that we actually now need to have parties who actually signed the transactions. Therefore, I'm prepared few set of parties I called nodes. So we have a OP, Nordea, and Lehman Brothers banks. Two of these banks happen to be also our customers. And then we have functions for signing and signing with the private key and verifying the signature by using the public key. How would we improve our system to include this? First of all, for transactions, we could record that we need to have signatures. So let's add this one here. The idea is that we store this inside the block where we have this hash verification. So now in here we say that we want to have these parties to sign this transaction. Otherwise, we think it's not valid. And then in the signatures, in the header, we will have a map of the signatures. And how would the signing then work? So if we now think about how would we sign a transaction, then let's take the, of course, now we have to fix this first. This is typically there are multiple signers. So we can use the identity. In our case, now the identity of the signer is just string. Of course, in real life, that would be something else. Let's use the same banks. The idea is that now I'm recording here that like these are parties who should sign the transactions to transaction be valid. And now, if we, for example, want to sign the TX transaction, we first have to get the block. Let's call it block from the TX, because this is what we want to sign. Okay, and then if we now just call this, it was called sign, yes, block, and then we take the take the private key from Nordia node, then this should what was the name? Sign. Yeah. Of course, this again needs the block in a serialized format. And now, ta-da! We all can see that this is a transaction signed by Nordia. And then, since we now have the signature here, then we could actually then call this signature. Signature, I'm formatting code a bit. Okay, now we have the signature, and now we had to update the transaction. So update the transaction. In here, what we want to update is signatures. We pass Nordia, which was the, and then the signature is what we want to update in that one. So now this transaction has also signature from one of the required signers, and then basically this can be used for checking that actually this transaction that we know that this was actually a Nordia who we are making a transaction with. Let's create sign TX function where we actually we need transaction, then we need, we can pass this node by just destructuring ID and key. I think, yes, and then we can just copy paste this part here and here, and yeah, now of course, yeah, we already have the private key here, so we don't have to use it like this. Everything is yes, and okay, then of course here should be ID. And now we can sign the transaction PX with one node again. Parent. Okay, we have issue. Let's do that. Signature. Yes. Okay, we are at the function. Okay, now I could improve the validate chain function in a way that we also in here always validate that all the required signers have signed the transaction by using public keys of those. But I think I just add this as verify signature, and this here added bonus, like, because I want to show another feature which is important in here, which is that since we are making transactions, then it's also important to know what we are actually doing. So typically there is some business involved. So the idea is that this blockchain also has some validation mechanism that we are following a certain rules. And typically it means that inside the block there is some code. In Bitcoin, it's, I don't remember even the name of the language, but it's stack-based language as good as brainfuck, I would say. And then, for example, Ethereum has some solidity and what have you. But anyway, of course, in here, like you already know, that what we are going to use is, of course, Clojure. And in our case, I don't want to go into details how to serialize existing functions in Clojure. There, it's possible, but there are some tricks. So I think it's just easier that, like, if I just write the function here as string, you see soon how this could be used. Current transaction, current value. Okay, because this is our now actually checking the data, current data and previous data. It will always get that one as the input. And in our case, we can, for example, validate that current data is the same as previous one increased by 1. Not very meaningful, but it's easier to write here as string. And now, yes, we have our validation code inside the transaction, and we can use it for validating transactions. So So if we want to validate code, we actually give the current TX and previous TX and previous TX. And now we want to check that I want to run this code. So let's and now from the let's take it from the current transaction. For example, take the current transaction, and then take that block and take the validator. Then we use read string, and of course this awesome function called eval. And we should have now a function that we can actually evaluate. So if we run the validator function with we only need, of course, the value. So we have the boilerplate. We take it from the block and take the data and use the same previous transaction block and take the data here. There is some chance that this actually works. Block typo. Yeah, you can at least compile. So let's now try to verify that this code works. So let's not use sign here, but instead validate code. And now we want to run the TX and the Genesis. That code validation works. Whoa! And you can see from that if we change this to 3, then our new awesome validation code actually validates stuff. And then of course we should also add this validate code function here to check that when we have the chain, then the current transaction, previous transaction is, and when we validate the chain, we always validate. It also passes that test. So now we can actually here run the validate chain function for the chain, and since we are not following the rules, then this should not pass. But if we create actual transactions, then like follow the rules we have inside the blockchain, then this passes. And now, if you think about how to use this blockchain, then the idea would be then just like if you think about in real world, then we would have, for example, Nordia chain, which would be just of course we use atoms if we want to change, and then we would have a OP chain and atom and so on, and then we generate these transactions, and then instead of creating this chain here, then we have some mechanism for sending these transactions to chains, and then those typically should run in different processes. Then they can validate those, so we can put swap Nordia chain and then put the Genesis transaction there and so on, and then transaction, and then there will be start building our blockchain, and then we can validate, for example, this Nordea chain that it is valid. Yeah, and then we can do the same thing with OP chain and somehow magically send these transactions to different nodes where they can do the verification. I don't have time to code the last feature I was thinking of, but at least I can mention then that now there is one more very important concept in this private blockchains, that you might have heard the double spending issue. So, like, let's say there's one for example, if we want to create like, let's say there is this guy, this Lehman Brothers happens to create a transaction. Of course, it can create a duplicate transaction. So this is also based on Genesis, and this one is also, this transaction is also based on the Genesis transaction. So now it's very, and if like this is a distributed network, and then when the parties start sending the transactions, there is an issue that even though you generate valid transactions and there are valid all the valid signatures, you can still create a situation where there is possibility that you don't know what's going to happen, that which one of these chains is actually valid. And one solution, like in Bitcoin, they use mining. In here, we can use, for example, notary. And the idea in notary is just very, in our case, it's very simple. We can actually just have, for example, a list of spent transaction hashes. And this way, stored somewhere, and this way, whenever the transaction, before we put anything in the chain, we actually notarize the transaction, meaning we send the transaction to the transaction hash, to the hashes, like the previous one also, to this notary, and this notary will mark the previous hash as spent. So this way, then it means that if this transaction now is run through the notary, this notary will spend the hash of the Genesis transaction. And then when this guy tries to do this one, then the notary says that, hey, you are trying to build a transaction on top of this transaction where this transaction hash is already used. And why we use hashes in this is that then the notary does not need to see the transactions. And then that the whole idea in this distributed network is also that it is decentralized. We have some central authorities, but they don't know the internals of the actual business at all. So in this case, the notary only sees hashes and says, like, this hash already used. And that solves this double spending issue in this private blockchain. So I think this is so awesome blockchain already. So it's on par with the product we already use almost. So I think it would be nice to go to the questions.
Okay, so my job was to monitor the questions and collect them, but I think we got exactly one question, and it's from Tommy. Tommy from Methosin. So do you, Tommy, want to ask it yourself, or? I guess finding the unmute button is so difficult that I can ask the question. So,
sure.
So what happens if the validator function was just a function that calls system/exit?
Yeah, that's a very valid question. The reason, for example, why the Bitcoin uses their own language, which is very limited. For example, it's not Turing complete language, and it doesn't even has any means of loops. So therefore it cannot hang. There is no way it hangs. If you use something like Clojure, you will end up in this kind of situation. And what actually has to happen is that if, like, for example, the product we are using, there has to be some pre-processing or then sandbox version of the JVM, for example, which prevents using certain concepts. So that's actually this my solution is pretty ideal. The idea is that somehow, for example, we should be able to parse the code and say that these are the valid functions from the Clojure that you are able to use in this. And the same thing goes that it should be deterministic. So the idea is that that all the nodes should run them in whatever time they have it. So also you cannot use any time functions or what have you. It should be always deterministic.
Tommy here. So I finally found the unmute. So I think Vincent already mentioned that, but there's the small Clojure interpreter, and that's the subset of Clojure, and it has these always terminating options, and you can define which sets. So it's like the sandboxing library.
Cool.
We are using that, for example, in Malli. So we are serializing the support functions, and they work in ClojureScript and Clojure and GraalVM too. So check it out. It's awesome library, but you can do everything with that, and it has all the options you need.
Yeah, great. This actually solves that issue that it should be limited set of functions to use.
Yeah, and I posted another question by myself when you were talking about the double spending problem, and you mentioned a notary that could be so that there could be a centralized notary. So could that notary also be a blockchain, or who is controlling? Can we have same guarantees as with the blockchains for the notary, or if the notary is a blockchain, should that also have a notary, and so on, and it becomes an infinite chain of blockchains and notaries?
Yeah, I think this is an endless loop that you can internally use this blockchain format, but of course if you want to run multiple notaries, then you need some mechanism, and you can use the blockchain, then you need it again. So I think usually, at least, there are some other mechanisms for syncing them. But for example, the notary is not, but I think this is also same kind of issue. If you think about these public and private keys, typically you also have to trust to some kind of a central authority. Like now I have, in my example, I just generated the private keys with OpenSSL, but in real life, all the participants in blockchain should trust some central authority that actually gives the certificates, and you should also verify the just that the signature is correct, but you should check that the signature is the signature is from that root central authority. So there are those few pieces you actually need, and they are implemented by not having a blockchain. I guess the certificate authority doesn't use blockchain either. It's some traditional.
Yeah, so is it then just shifting the I've understood that one of the value proposition of blockchains is that you don't need to have the central authority to verify the transactions, or that the authority it is public and anyone can like check it, but you don't have to trust any like a bank or anything like that. But you can just get the data and run the verifications yourself. But if we still need to trust the certificates that are issued by some central authority, then are we just shifting the authority issue to some other place, or what is going on there?
Yeah, of course, yeah, that's more like a business decision, but I think this is an important thing, that in public blockchain you want to have some kind of this kind of censorship prevention also, that the government cannot do anything, or like some but in here, if the places where you use these private blockchain things is more like that. For example, if you have many banks or financial, like, and you're doing important transactions, then you might not want to have one central database. Like, all the participants in the network are fierce competitors of each other. So the challenge is that they don't want to have a central database who sees all the transactions and stores, and there's all kind of compliance and regulatory reasons. So now, if you have these kind of central authorities that have very limited responsibilities, like this certificate authority and this notary who just checks that if hash is correct, then it opens up new possibilities for example, like banks to work together. So it's different use case.
Okay, thank you very much. Now we got also another question from, no, this one is from Ykkä. What would be the biggest issues in creating a real-life production blockchain in Clojure?
Of course, Tommy already solved the issue of serializing the functions. I think it's more like that really doing all the stuff that I was showing there. There's quite a lot of functionality that it actually works in all cases and handles everything correctly. So I think I think Clojure would fit there, but it's really doing this kind of a product. It's quite a beast in a way. So the sandbox thing is the one thing where you can actually run the validation code. And I think, I'm not sure about this key library yet, because you should also be able to somehow stop the process. And so it's not just that you cannot use these functions, but how to prevent endless loops and how to do things like that.
In SCI, there's the loop prevention. So there's the always terminating flag, and because it doesn't use eval, it has its own interpreter. So you can say that for example, whatever you are looping, the max count is 100. After that, it fails.
Whoa. Okay.
Yeah, that's nice.
Yeah. Yeah. Yeah, but besides that, I think there's a hell of a lot of work. But
okay, I think we don't have any more questions.
Yeah, I can put this code to GitHub and to share after the session. Yeah. If someone wants to build their own product and based on the code.
Yeah, just fork it.
Yeah, exactly.
Okay. Hey, but thank you very much for a great presentation.
Yeah, thanks.
Maybe we could have a short break. The idea was to have the next presentations.
My name's Jaakko.